lava, lava forms and so forth. Secondary succession is where life progresses where soil remains. You can see clear-cut forest, old farm. Basically, if a system had an upset. All right, and let's look at a couple of examples of these. All right, this diagram should look somewhat familiar. I'm going to move this around a little bit. You can see here this is the pioneer community, the cereal stage, and so forth. But basically, this is primary succession. You can see what happens in terms of the development of the community. It's basically nothing into a full ecological community. Barren rock. This is where you start from beneath a retreating glacier due to a volcanic eruption. Low-growing plants such as mosses, ferns, and lichens begin to colonize. Fast-growing grasses this is in the pioneer community. The cereal stage, you can see, would be fast-growing grasses, weathering flowering plants, and small shrubs kind of appear and begin to take root. A thin layer of soil develops as as some rocks start to decay. And then again, as part of the cereal stage, and then for the climax community, you can see this is taking place over a long period of time. But basically, fast-growing trees such as a birch wood and mountain ash form a low forest, basically shade out the lower plants, and that would block the sunlight from the lower plants, so they would kind of die out. And in the climax community, 100 to 200 years since colonization began, large, slow-growing trees such as an oak become established. Then in terms of, we'd like to show you a little bit in terms of secondary succession here. And this is where you have an established climax community and some kind of an upset will occur here. This could be a forest fire, for example. And then trees can be, or plants that have been destroyed and animals have fled the burnt out area. A layer of ashes over the soil, you can see, just from the burning. After 3 to 5 years, the grasses and low-growing shrubs have colonized the land. About a generation later, small trees form a young woodland. And then 50 to 100 years after the setback event, the mature oak woodland is restored. So that would be an example of secondary succession. So I would just know the key differences between those. I think that's the main idea with succession. These next three basically are about, in effect, what we call symbiotic relationships. Is kind of, you scratch my back, I will scratch yours. And I thought we had a very, very fine session earlier in the year on symbiosis of the different relationships. I'll go over that sheet with you in just a minute. But basically, you've got mutualism, a symbiotic relationship where both organisms benefit. Commensalism, a symbiotic relationship where one organism benefits and the other is absolutely unaffected, has no impact on them at all. And a parasitism, where it's a relationship in which one organism, the parasite, obtains nutrients at the expense of the host. And many times, oftentimes, the parasite is very inhospitable to the host. Let's go ahead and look at a couple of these here. One would be here's a classic example, a dog and a flea. This would be an example of a parasitism symbiotic relationship. The flea feeds on the blood from the dog. There is no benefit to the dog, but yet the itching and bites may lead to infection. Mutual is fungus and algae. This would be a lichen here. The photosynthetic algae provide food for the fungus, which in turn provides a suitable living environment for the algae. This would be an example of mutualism. One of my favorite examples of mutualism is termites and the cellulose digesting bacteria. Great trivia question to share, where termites do not actually digest wood, but they do contain the cellulose digesting bacteria in their gut that does. Pretty cool stuff. A shark and a remora would be an example of what we call commensalism. where the remora fish swim alongside the shark and take scraps of food. You can see the shark does not eat the remora and appears unaffected by its presence. And a couple of others here, the cattle and the cattle egret. The egret follows herds of cattle. This would be commensalism. Eats the insects that the cattle stir up as they move through the grassland. And the cattle appears to be unaffected, absolutely unaffected by the egrets. And the other one would be a human and a tapeworm, an example of a parasitic relationship. Okay, back to our lists here. We are working on carrying capacity. This was from our very first, one of the first lab activities we did. Think of the fish who went fishing with the straws and everything. Again, a fee, but it does illustrate very beautifully the idea of carrying capacity, or the number of individuals that can be sustained in an area. One of the most important concepts in all of environmental science is carrying capacity, and it's really the key of our, as we've studied, I've said over and over, the big problem is population. Do we have the resources? Can we carry, if you will, the number of people that are coming into the world? Can we feed them? Can we house them? Do we have the resources to do that? An R and a K strategist, you might remember, is the reproductive strategies, in which we talked about this in terms of survivorship. And some types of organisms reproduce differently and manage their young differently. An R strategist would be a reproductive strategy in which organisms reproduce early, bear many small unprotected offspring, insect and mice. They really stay alive as a population because they have so many they reproduce. A K strategist, which would be us, as an example, humans and elephants, larger offspring. Reproductive strategy in which organisms reproduce late, bear few, really care for the offspring. So that's important with that. And then just a couple more here, then I'll conclude this particular video. Natural selection is really the whole vehicle, if you will, the whole mechanism of evolution. Organisms possess favorable adaptations that will pass them into the next generation, and kind of almost the survival of the fittest type thinking. Thomas Malthus was the one who was kind of the doomsdayer, who was very pessimistic on human population and can we continue to increase the population at the rates we have. He said we could not. He also said that the amount, because of the, we could not develop a policy. We wouldn't have enough land to feed this burgeoning population. That was his big thing. He said the consequence was going to be war, famine, and pestilence, disease. What Malthus was wrong, of course, was wrong. I think we discussed in class because of technology. He could not have foreseen the amazing advances we've made in plowing and seeding and in harvesting crops. He could not have seen the amazing advances in fertilizers and whatnot. So Malthus was the doomsdayer. Said we weren't going to make it, but we are. He was proven wrong. And the last one I want to talk about here today is doubling time, which is the rule of 70. If you remember, the doubling time equals 70 divided by the present growth rate. So as an example, a population growing at 5% annually doubles in 14 years. I am certain you will get at least one question on this. This should be an easy one to pick off. You just take the percent, divide it into 70. You can't use a calculator, but you can at least get a rough idea. And this would give you the number of years it takes to double. So a 5%, for example, if you had $10,000, all right, earning at 5% return on your money with interest in 14 years, you would now have $20,000. So it's pretty cool. It's really, the economists use this as kind of the growth of money. Environmental scientists use it in terms of growth of populations and stuff. All right, we will stop there. Thank you.